Imagine you could step into a time machine and travel back exactly 20,000 years.
Which, in geological time is basically nothing.
Right. It's just a fraction of a blink. I mean, modern humans are already walking the Earth. We're painting those incredible scenes in caves. We have music, complex tools.
But the world itself, it would look entirely alien to us today.
Exactly. Because, well, you look up, and sitting directly over what is now Canada and the northern U.S. is just this solid, towering sheet of ice.
Yeah, and we were just talking about a bad winter frost here.
No, we're talking about an ice sheet up to 3 kilometers thick. Just 3 kilometers of crushing weight. And it wasn't just North America either.
Right. Northern Europe was buried too.
Yeah, if you tried to stand where London or Berlin are today, you'd be trapped under thousands of feet of permanent blue ice.
And, to build ice sheets that massive, all that water had to come from somewhere. It came directly from the oceans.
Right. It evaporated, fell as snow, and just never melted.
Exactly. So because so much of the Earth's water was literally locked up on land, global sea levels were drastically different. They were roughly 120 meters lower than today.
Which means the maps we rely on just completely wouldn't apply. I mean, you could have walked on dry land all the way from Asia to America across the Bering Land Bridge.
You could stroll from the Australian mainland right over to Tasmania without getting your feet wet.
It's wild. And this was the absolute peak of the last frozen era. So the mission of our deep dive today is to explore this reality because this frozen world didn't just happen once in some freak accident.
No, it's happened over and over again on this strikingly regular beat.
Yeah, so today we're going to unpack the astronomical clockwork that controls that rhythm.
And this journey is just so essential. I mean, what's at stake here is far more than just trivia about woolly mammoths.
Oh, for sure.
Understanding this deep past is basically the ultimate key to understanding the climate machinery of our present. It shows us how the entire planetary system operates when you start, aggressively pushing its buttons.
Okay, but before we get into how a planet freezes, we need to clear up a massive popular misconception.
Oh, definitely. The terminology trips everyone up.
Yeah, because when I hear Ice Age, my brain instantly goes to the movie version. I picture the whole globe covered in frost, eternal blizzards, just a total deep freeze.
Right. But scientifically speaking, that pop culture image is actually entirely misleading.
Okay, let's unpack this. What is the actual definition then?
So, using the strict scientific definition, an ice age is simply any period in Earth's history where there is permanent ice at the poles. That's it.
Wait, permanent ice at the poles. But Greenland has a permanent ice sheet, and Antarctica is totally covered in ice.
Yeah.
Are you telling me that scientifically I'm sitting in an ice age right now?
You are firmly inside an ice age right now. We have been for a couple of million years, actually.
That is, wow, that completely flips the whole cultural narrative on its head.
It really does. What you're picturing with the mammoths and the 3-kilometer-thick ice burying New York is more precisely called a glacial period.
Okay, a glacial period.
Right. It's a specific, intensely cold phase that happens within a larger ice age. It's when those polar ice sheets aggressively advance and crush the continents.
Okay, so if the freezing mammoth-heavy part is a glacial period, what do we call the phase we're in today? Because I definitely don't see any glaciers advancing down my street.
We are in what climatologists call an interglacial period. Basically, these are the relatively brief, warmer gaps between the deep freezes.
The ice retreats, sea levels rise.
Exactly. The planet gets a bit of a breather. And our current interglacial gap began about 11,500 years ago.
That timeline is genuinely staggering to think about.
It really puts things in perspective.
It does, because all of human civilization, I mean, the invention of agriculture, the first cities in Mesopotamia, writing, the Roman Empire, smartphones, all of it fits entirely inside this one brief, mild interglacial window.
It just highlights how delicate our global civilization really is. For millions of years, the Earth has been trapped in this rhythm.
Cycling back and forth.
Right. Brutal glacial phases lasting tens of thousands of years. And then these very brief warm gaps. We just happened to build our entire society during one of the warm gaps.
Which introduces a massive mystery, honestly. If human history is just a warm gap and a deep freeze, what actually flips the switch?
That is the million-dollar question.
I mean, we're talking about moving oceans of water onto land and freezing them. What kind of force can reliably turn an ice age on and off?
Well, The answer comes from the sky, and the guy who first figured this out was a Serbian mathematician named Milutin Milanković.
Okay.
His story is pretty incredible. During the First World War, he was actually interned as a prisoner of war.
Wow, really?
Yeah, and while he was a prisoner and for years afterward, he just dedicated himself to calculating the Earth's orbital variations by hand, with paper and a pencil.
Hold on. You're telling me a mathematician sitting in a World War I internment camp was doing hand calculations to figure out the climate from hundreds of thousands of years ago?
That's exactly what he did.
How could he possibly know what the Earth's orbit was doing before human beings even existed?
Well, celestial mechanics are incredibly predictable if you know the physics. His core insight was that the Earth's journey around the sun isn't a static, unchanging loop.
Right. It's not a perfect track.
Exactly. It gets tugged on. Massive planets like Jupiter and Saturn exert their own gravity on the Earth. So over tens of thousands of years, that gravity slowly warps our orbit.
And as our orbit changes, it slightly shifts exactly how and where sunlight hits the planet.
Yes, and he broke this shifting down into 3 distinct orbital cycles.
Let's walk through them because this is really the clockwork of the ice ages.
Yeah.
Cycle number 1 is the shape of Earth's orbit, right?
Correct. So it isn't a perfect circle. Over about 100,000 years, the gravity of those other planets slowly stretches our orbit out.
So it becomes slightly more elliptical, like a stretched oval.
Right, and then it slowly relaxes back into a more circular shape. That's the first cycle.
Got it. And the second cycle is the tilt of the Earth's axis.
Yeah. The Earth isn't perfectly straight up and down. It's tilted, which is why we have seasons. But that tilt isn't permanently fixed.
It changes over time.
It does. Over roughly 41,000 years, the Earth slowly nods back and forth, changing its tilt from about 22 degrees to 24.5 degrees.
So a steeper tilt would just mean more extreme seasons, right?
Exactly. The summer hemisphere points more directly at the sun, and the winter points further away.
Okay, and the third cycle is the wobble.
Yes, the wobble.
If you've ever watched a toy top spinning, you know it doesn't stay perfectly upright. As it spins, the top of the axis slowly wobbles around in a circle.
The Earth does the exact same thing. It takes about 23,000 years to complete one full wobble.
And what this wobble does is change which season we're experiencing when the Earth is at its closest point to the sun in that slightly oval orbit.
Right. And when you put all 3 of these together, you have to remember one crucial fact. None of these changes actually alter the total amount of solar energy hitting the Earth.
Wait, really? The total amount stays the same?
Pretty much, yeah. The sun isn't getting hotter. We aren't moving drastically closer to it overall. What changes is purely the distribution.
Okay.
It alters the timing and the specific latitude of where that sunlight lands.
So, to visualize this, I'm picturing these 3 cycles, the shape, the tilt, the wobble, as 3 different metronomes sitting on a desk.
That's a great way to look at it.
Right, so one metronome is ticking every 100,000 years, one every 41,000, and the third every 23,000.
Totally out of sync most of the time.
Exactly, they're a chaotic mess. But eventually, if you wait long enough, there comes a specific moment where all 3 metronomes finally click on the exact same beat.
And that alignment is exactly what Milanković was looking for. He calculated when those celestial metronomes align to create one very specific condition.
Which is?
Exceptionally cool summers in the Northern Hemisphere.
Okay, wait. That feels entirely backwards?
Yeah.
If I want to build a giant glacier that buries Canada, my brain instantly thinks I need the most brutal, freezing, apocalyptic winters possible.
Right. It's totally counterintuitive.
Yeah, so why is a cool summer the trigger for an ice age?
It's all about geography. To understand it, just look at a globe. The vast majority of the landmass where an ice sheet can actually grow is mostly in the Northern Hemisphere.
Right, you've got Canada, Siberia, Northern Europe.
Exactly. Antarctica is massive, sure, but it's isolated at the bottom of the world, surrounded by ocean. To change the global climate, you need ice spreading across northern continents.
Okay, we have the real estate in the north. But that still doesn't explain why the freezing winters don't matter as much.
Think about the winters in northern Canada right now. It is already dangerously cold. It's more than cold enough to snow.
That's true.
Making the winter even colder, like dropping it from -30 to -40, doesn't fundamentally change anything. The snow is already guaranteed.
So the critical vulnerability for a glacier isn't the winter at all.
Nope, it's the summer.
Oh, the snow has to survive July.
Precisely. If the summer is just a little bit too cool to melt away all of the previous winter's snowfall, a layer of snow survives into the autumn.
And then the next winter arrives and just dumps a fresh layer on top of it.
Exactly. The pile never resets to zero. Year after year, it accumulates. And the sheer weight of those layers compacts the bottom into dense, solid ice.
So warm summers mean the slate gets wiped clean every year. But cool summers mean the snow compounds into an ice age.
Yes. And Milanković predicted that whenever his 3 metronomes aligned to deprive the north of summer heat, the ice would build up.
It's an incredibly elegant mathematical theory.
It really is.
But, I mean, it's just math on a piece of paper, right? He's doing this a century ago. A guy with a pencil claims he knows the global temperature from 200,000 years ago.
The scientific community definitely didn't just take his word for it.
Right. I mean, we needed physical proof, but time machines don't exist. How did anyone actually verify this?
Well, it took arguably the greatest piece of scientific detective work of the 20th century. We needed a physical record of the Earth's atmosphere, and we found it hiding in the ice itself.
Wait, you mean we just went out and dug up ancient ice?
We drilled for it, yeah. In places like deep Antarctica and Greenland, it has been snowing for hundreds of thousands of years, and it never melts.
It just packs down.
Right. So scientists go into these freezing landscapes and drill hollow tubes deep into the ice sheet. When they pull it up, they extract this long cylinder called an ice core.
Because the layers build up year after year, pulling up an ice core is literally pulling up a physical column of frozen time.
Exactly. It's like tree rings. The deeper you drill, the older the ice.
Okay, but a block of ice is just frozen water.
Yeah.
How does frozen water act as a thermometer for 100,000 years ago?
This is where the chemistry comes in. Water is made of oxygen and hydrogen. But not all oxygen atoms are identical.
Oh, like isotopes?
Yes. Most oxygen is a lighter version, but a small percentage is slightly heavier.
So you have heavy water and light water.
Precisely. And think about evaporation. It takes heat from the sun to evaporate water out of the ocean so it can eventually fall as snow.
Okay, I fell.
Because those heavier molecules weigh more, it takes slightly more heat energy to lift them out of the ocean.
Ah, I see where this is going. If the global climate is really cold, there isn't enough heat energy to evaporate the heavy water molecules. They just get left behind in the ocean.
You nailed it. The mechanism is foolproof. Scientists melt a slice of ancient ice, measure the ratio of heavy to light water, and if there's very little heavy water, it proves that specific year was intensely cold.
That is just brilliant. But there is something else trapped in that ice, isn't there?
Yes, there is.
Because as the snow gets crushed into solid ice, it traps air.
Right. Microscopic bubbles of air get completely sealed in the ice, and those bubbles aren't a guess or a proxy. They are direct, pristine, physical samples of the Earth's atmosphere from the exact moment that snow fell.
They're like tiny frozen time capsules of ancient breath.
That's a beautiful way to put it. We extract the air from those bubbles and measure precisely how much carbon dioxide was in the atmosphere 800,000 years ago.
So we extract the ice cores, measure the temperature using the heavy water, and measure the CO2 using the bubbles.
Yep.
We build this massive timeline. And when we lay that physical record over Milankovic's hand-drawn predictions,
it matches flawlessly.
wow.
The physical evidence proved that the ice sheets advanced and retreated in exact rhythmic time with the orbital wobbles he calculated.
That is an incredible triumph. But, digging into this reveals a glaring logical problem.
Object energy problem.
Yeah. We established that the 3 metronomes don't change the total amount of sunlight. They just shift it around slightly.
It's just a tiny celestial nudge.
Right. And a tiny nudge in summer sunlight simply cannot possess enough raw energy to bury a continent under 3 kilometers of solid ice. The math doesn't add up.
And physics completely agrees with you. The orbital cycles alone are profoundly weak. They might drop the temperature by a fraction of a degree.
So how does a fraction of a degree cause an ice age?
They require a mechanism to amplify that tiny nudge into a planetary catastrophe. They require climate feedbacks.
Feedbacks. We hear this term constantly in modern climate science.
Basically, think of it like a microphone and a speaker.
Okay.
If you whisper into a microphone, the speaker amplifies it. If you put the mic too close, it catches its own amplified whisper, feeds it back in, and suddenly it escalates into a deafening screech.
So how does the Earth create a feedback loop like that?
The first major amplifier is reflectivity, which scientists call albedo. It's just a measure of how much sunlight a surface bounces back into space.
Like wearing a black shirt versus a white shirt on a hot day.
Exactly.
Yeah.
Dark things like forests or the ocean have low albedo. They absorb heat. White things like snow and ice have high albedo. They act like a giant mirror.
Okay, so the celestial metronomes line up, provide a tiny nudge of cooling. A little extra snow survives the summer in Canada.
And because that new snow is bright white, it reflects the sun's energy back out into space. That patch of land isn't absorbing heat anymore.
Which makes the surrounding air slightly colder,
Yes.
which means the next year, even more snow survives, the white patch grows larger.
The mirror gets bigger.
Wow. It reflects even more heat away, aggressively dropping the temperature, creating even more ice. The whisper turns into a screech.
That is the albedo feedback. But there is a second, far more powerful feedback loop, and it involves the oceans.
Okay, how does the ocean fit in?
As the planet cools from the ice mirror, the oceans also start to chill. And here's a fundamental law of chemistry. Cold water can hold much more dissolved gas than warm water can.
Oh, it's the same reason a warm soda goes flat immediately if you leave it in the sun. But a cold soda kept in the fridge stays fizzy.
A perfect analogy. As the global oceans cool, they act like a massive sponge, aggressively pulling carbon dioxide out of the atmosphere and dissolving it into the cold water.
But carbon dioxide is a greenhouse gas. It traps heat in the atmosphere.
Right. So as the ocean absorbs the CO2 out of the air, the Earth's thermal blanket gets thinner.
The atmosphere loses its ability to hold onto heat. The planet plunges into an even deeper freeze, making the ocean even colder, which lets it suck even more CO2 out of the sky.
You've got it. So the Earth's orbit is just the person lightly tapping the first domino.
But the reflective ice and the CO2 are the actual heavy machinery doing all the physical work of freezing the planet.
Exactly. And the ice cores confirm this mechanism with terrifying clarity. Across 800,000 years, CO2 and global temperature move in absolute, unbroken lockstep.
Wow. When CO2 drops, the temperature plummets. When CO2 rises, the temperature spikes.
Always.
Okay, so if the sky controls this whole natural rhythm, it inevitably leads to a massive question about today.
I know exactly where you're going with this.
Because, I mean, a really common argument is, look, the climate has always changed naturally. You just explained how ice ages come and go based on orbits. So modern warming is just another natural swing, right?
It is a totally understandable assumption, honestly, if you only look at half the picture. But when you examine the full ice core record, it completely demolishes that argument.
It does.
Completely. The history of the ice ages doesn't reassure us that modern warming is natural. It explicitly warns us that it isn't.
Let's break down exactly why the ice cores destroy that argument, because this is crucial. Point number one has to be the sheer speed, right?
Speed is the great biological filter. When we look at natural cycles driven by Milanković's clockwork, they are agonizingly slow. The transition from a deep freeze to a warm period takes roughly 10,000 years.
Right, so a forest can't pack up and move. But over 10,000 years, an ecosystem can slowly migrate further north. Animals have hundreds of generations to evolve and adapt.
But the warming we are subjecting the planet to right now is happening over a century or two. We are taking a 10,000-year warming phase and compressing it into a single human lifetime.
It's dizzyingly fast.
By biological standards, it's violently destructive. Ecosystems just cannot migrate or evolve fast enough to keep up.
Yeah. And point number two is the actual trend we're supposed to be on right now.
Yeah.
Because if we check the three celestial metronomes today, the shape, tilt, and wobble, what are they telling the Earth to do?
Well, if humans had never discovered fossil fuels, the natural orbital cycles are currently nudging us gently toward a cooling phase.
Wait, we should be cooling right now.
Yes. Over the next several thousand years, we should be sliding back toward the next deep freeze. The natural trajectory is cooling, but instead, the planet is experiencing explosive warming.
So we are literally swimming directly against the astronomical current.
We are fighting the sky, and we are winning. Which brings us to the third and most critical point, the control knob.
Right.
The deep past proves beyond any doubt that carbon dioxide is the primary amplifier. It's the master control knob for the global thermostat.
And right now, by burning fossil fuels, we've injected massive amounts of it back into the atmosphere.
Exactly. The concentration of CO2 has shot higher and faster than anything seen in the entire 800,000-year ice core record.
So we took the microphone, hooked it up to the biggest amp we could find, and cranked the volume dial to 11.
Pretty much. The deep past isn't a comforting reassurance that everything is fine. It is the ultimate warning label on the climate machine.
It proves that CO2 dictates the temperature, and we're turning that knob harder and faster than nature ever did.
Because the fundamental physics haven't changed. The greenhouse effect works exactly the same today as it did 200,000 years ago. The only variable that has changed is who is operating the machinery.
That is, wow. Here's where it gets really profound. The next time you look at a map of the world, I really want you to see the ghosts of the ice.
Yeah, those invisible
All
connections.
right. When you notice that narrow stretch of water between Britain and France, or the shallow sea between Alaska and Russia, remember that those maps are temporary. Human beings, people just like us, walked across those gaps on dry land.
They live their lives on the edge of a world dictated by the slow ticking of a celestial clock.
It's an incredible piece of planetary machinery.
It is, and it leaves us with a profound, almost existential reality to mull over. I mean, every empire we've built, every technological leap, only exists because the Earth's orbit happened to grant us this brief, fragile window of warmth.
Yeah.
So what does it mean for the future of our species now that we have taken the climate control knob out of the hands of the cosmos and put it directly into our own?
A heavy but totally essential question to leave lingering in the air. So take a look outside at this rare, beautiful interglacial world we inherited, and just remember the massive forces operating out of sight. Thanks for diving deep with us today, and we'll catch you on the next one.